Welcome back to Finite Element Methods. So class number 9. Last time we were talking a little bit about the 2D finite element method, or at least we were starting to explain the rudiments of that. We explained what we mean by a triangulation, an admissible triangulation of a polygonal domain in 2D. And so the basic idea is we want to allow pretty flexible looking meshes in 2D for polygonal domains, but we have to have certain rules in place. One of which is that we can't have situations like this where we have what's called a hanging node. So in this case, if we took the intersection of two triangles that actually have a non-zero intersection, let's say these two. Of course, triangles, the way we define them, are going to be open sets. So we have to take the closure and then we have to, of each one of those, and then we have to take the intersection. So the intersection of these two triangles here and here is this line there, which for it to be an admissible triangulation of this domain is just a diamond shape. For it to be an admissible triangulation, that intersection would have to be a full edge. Okay, in this case, it's only a half an edge or partial edge. Well, it's a full edge of this triangle, but for this triangle, it's only a partial edge. So this would not be admissible. However, there are often ways, pretty simple ways of fixing these triangulations up so that they do become admissible. For example, in this case, we can just make a very simple connection as like the one I just drew, and then we don't have any hanging nodes anymore. So that was the basic idea about admissible triangulations or triangulations in 2D. They had to have certain properties. So have a look at this mesh here that I've drawn. This is a polygonal domain where we've got a bunch of triangles covering it. And we want to break the points of the triangulation into different categories and classes. So let's start off by our assumptions. We start off with a triangulation which doesn't have any hanging nodes of this polygonal domain omega, and we're going to define this set V, which is the set of all vertices of every triangle in the triangulation. The set of all x such that x is a vertex of the triangle K for some K in the triangulation. So that's going to give us these blue points, and it's also going to give us these yellow points on the boundary. They're vertices, okay? So the set of all those things is just called script V. This is called the vertex set. Now we're going to define another set, which is not all vertices, but is the most important ones for our um, model problem, and that is the set of interior vertices. So that's going to be labeled V0, V superscript 0, and it's going to be equal to or defined as the intersection of V with omega. Remember, omega is an open set. It does not contain the points on its boundary. So whenever we take the intersection of V with omega, it's going to drop these orange points. These are the so-called boundary vertex set or boundary vertices. So the interior vertices are just these blue points. 1, 2, 3, 4, 5, 6, 7 of them. Those are the points. And actually, what's in there are actually the coordinates of those points. So this is the interior vertex set. The elements of V are just called interior vertices. Those are the blue points. And that's going to be to distinguish those from boundary vertices. So the set of boundary vertices is labeled partial V, So that's our usual symbol for boundary. I'm not sure why it's a standard symbol for boundary, but it has become so. Um, so partial V, that's going to be the set of all vertices minus the set of interior vertices. So that leaves only the boundary vertices left, or in other words, the orange points. Now let's define the following set of points. The set of points E. This is going to be the set of edge midpoint nodes. Now, we're not going to call these vertices because vertices are only at the corners of triangles. These points, these red and green points, are going to be at the midpoints of an edge. So for example, let's look at missing a point, aren't I? Yeah, right. A couple of them actually. Let's see if I've missed any more. I think I got them all now. Okay, so these red points are these are points where we simply are taking two neighboring vertices and we average them. Okay? We average their coordinates. These two vertices have to be in the same triangle. Okay? They have to be within the same triangle. So let's see if I've got my definition correct for these red points. Okay, so I'm trying to define these points here. They should be the set of all x which are equal to this average. X1 and X2 are not equal to each other, but they're points that are in the vertex set. Okay, they're in the vertex set and they're in a triangle for some triangle. Okay, so that's exactly what we mean by these edge points. We're looking for points that are in the vertices or in the vertex set, like let's say these 2 points here, and in the same triangle, and then I'm going to average them to get this red point. Okay, so a set of all those red points and also these green points, because we're not restricting ourselves at all in the way we're defining this, are what we call this set E. Okay, so the red and the green points, red, green. Now, of course, we can go through the same playbook. We can take the intersection with omega, and that's going to get us the interior edge points. Okay, interior edge points. Edge midpoints, I guess we should call them. And then of course, if I take all the edge midpoints and I subtract off the boundary edge midpoints, then that will, or sorry, the interior ones, that leaves only the ones on the boundary. Okay. So apart from the fact that I missed a few when I was labeling these, um, I think I've got them all now. But if you see that I'm missing any further ones, you can fill them in. Okay, so the set of all interior vertices are the blue points. The set of all boundary vertices are the orange points. The set of all interior edge midpoints are the red points. And the set of all boundary edge midpoints are the green points. Okay, so those sets are useful to have distinguished from each other. Okay. Okay, so let's now that we have all these points and these this setup, we can define our piecewise spaces in 2D. We can also define our basis functions in 2D. So again, suppose that we have a triangulation of a polygonal open set omega. We're going to define the piecewise polynomial finite element spaces for R in N. In this case, we don't have to restrict R in any way. Later on, I'm only going to to define the basis functions for r equals 1 and 2. So this is r for r being any counting number, so 1, 2, 3, unlimited. We're going to define piecewise polynomial spaces in the following way. So MR are these functions that are globally continuous. So this is what we mean by globally continuous, C0 omega bar, such that if I restrict V to any triangle, it's going to be a polynomial of degree R on that triangle for every triangle in the triangulation. So that's the big space. And then I'm also going to want to restrict that space for our model problem. So for our model problem, it turns out that it's useful to restrict this space to a subspace of functions that are 0 on the boundary. So this is always my notation for these function spaces which are 0 on the boundary. Okay, so what we want to show ultimately is that this is a finite dimensional subspace of H1. And this is a finite dimensional subspace of H01. Okay, finite dimensional, sometimes I write like this, subspace of H01. And this is going to be a finite dimensional subspace of H1. How do I know this? Well, this next theorem guarantees at least this part, and then I can use some reasoning to get this fact. Let tau be a triangulation of omega, and suppose that V has the property that if I restrict V to any k, or the closure of k, and I find that that guy is C infinity on that closure for all triangles in the triangulation, then V is an HL function, a Sobolev HL function. That means it has L weak derivatives, which are also L2 functions, if and only if V is globally CL minus 1 over omega bar. Okay, so if I want to know that a particular space has a certain amount of regularity, certain number of weak derivatives, then I need to know two things. I need to know its regularity I need to know the regularity on each triangle and its global regularity in terms of its classical differentiability, because this is an if and only if result. So if I go back to these two spaces here, what is it saying? Well, both of these two spaces are just going to be C0 spaces. So at best, these functions from this set can be H1 functions because I have C0 here. I can set L equal to 1. L minus 1 is just 0. So globally C0. So the best that these functions can be is H1. And then what's required to show that? Well, the functions, when I restrict to any triangle in the triangulation, have to be C infinity. Well, of course, polynomials are C infinity functions, so that's not an issue at all. So this theorem tells us right away that the functions of this class are going to be at best H1 functions. Now, even if I make R larger and larger, it's not going to give me smoother and smoother Sobolev functions. At best, they're going to be H1. If I really want H2 or H3 piecewise polynomial spaces, then I have to modify this restriction here. To get a piecewise polynomial space, which is C1, I'm going to need, that is H2, then I'm going to need this to be C1. I'm going to need it to be globally C1, which is a fairly difficult thing, it turns out, in finite elements to produce. Now, What we're ultimately going to show is that MR and M0R are non-trivial proper subspaces of H1 and H0. And so what that means is there are things in them. And furthermore, we're going to show that these are finite dimensional. And not just that, we're going to build bases for these. So this turns out to be a key concept for what we're doing in this course. Our piecewise polynomial spaces are going to be our workhorses for this further approximation theory that we're going to develop. These guys are going to be subspaces of H1 and H01 respectively. Well, how do we show that these guys have that they're non-trivial proper subspaces of the dimension that we want? Well, the easiest way to do that is to exhibit a basis for these spaces. So let's build bases for both this space and this space. Now, if I wanted to build bases for, let's say, M3 or M4, I would need more information. And I'm not going to worry about that. Not too much for this course. I am going to speak a little bit about it at some point. So I'll speak about the case where R is greater than 2. Let's say for piecewise cubic spaces, in that case, R is 3. Piecewise quartic spaces, R would be equal to 4. Quintic spaces, R equals 5. I'll say a little bit about those, but not too much. We're going to mainly focus on the piecewise linear and the piecewise quadratic spaces. I need a little bit more information, a few more pieces of machinery before I get into that. So let's again let tau h be a triangulation of our polygonal domain, omega, in R2. I'm going to define N1 to be exactly, so this is a script. This is supposed to be a calligraphic N, okay? And I'm going to try to do my best to distinguish a calligraphic N from a standard Roman N. So this calligraphic N1, that's the set of all vertices, okay? The set of all vertices. N2 is going to be the set of all vertices and union with the set of all midpoint, let's see, edge midpoints, okay? Edge midpoint nodes, I guess. So these are vertices and these are edge midpoint nodes. So if I union those two together, that's going to give me a set of points, and that set of points I'm going to call calligraphic N2. The number of points in this set is what I'm going to call N1. That's the number of things in there, also called the cardinality of the number of points in calligraphic N1. And likewise, N2 is going to be the number of points or the cardinality of the set calligraphic N2. Now, those two spaces are useful. These ones down here are slightly more useful from our point of view because of the model problem. The model problem has zero or homogeneous Dirichlet boundary conditions. What do I mean? I mean that we're eliminating as degrees of freedom the functions on the boundary. And so what that means is in the end, I don't have to build basis functions owing to or basis functions with respect to the points on the boundary. That's a very important distinction. So I only need to work in that case with this nodal set, okay? So N01, that's the set of all vertices that are in the interior, the set of all interior vertices. And the number of those points is what I'm going to write as N10. N02, calligraphic N02, that's the set of all interior vertices, union with the set of all interior edge, let's see, edge midpoint nodes. I have a hard time saying it or remembering what it is. Edge midpoint nodes, but they have to be interior. Okay, interior, interior, and I'll show you in an example what's going on here in just a minute. The number of objects in this set is what I'm going to call n20. Okay, n20. And now it's a similar game that we play that we played in to that which we played in one dimension. We're going to define basis functions, and now I'm going to define these kind of for any r, well, for r both or possibly equal to 1 or 2. They can't simultaneously be equal to 1 and 2, but so take r being 1 or 2. The reason why I'm saying 1 or 2 is because my definition here is not going to work for r equals 3 or 4 or 5. I need more information about the mesh than what I've extracted. All right, so the basis function phi r I from mr, r equals 1 and 2, for I between 1 and nr. So I'm foreshadowing the fact that the basis is going to have exactly nr elements in it. It's just defined in the following way, which completely describes how these basis functions look and are and how they work. Phi ri zj is equal to the Kronecker delta symbol delta ij. And the best way to figure out what the heck this means is through some examples, which I'll give you in a minute. Okay, so this ZJ, that is the set of all nodes in my mesh. Okay, now the nodes consists in whenever r equals 1, the nodes are just the vertices. What about whenever r is equal to 2? In that case, the nodes are the vertices and the edge midpoints. Okay, whenever r is equal to 1, the nodes are just the vertices. Whenever r is equal to 2, the nodes are the vertices and the edge midpoints. These functions are in the space and they satisfy this condition. And my claim is that this uniquely and completely defines what these functions look like, what they are. That there's nothing else to do except to define them this way. And I hope to show you that or convince you of that through pictures. Okay, so again, these are the basis functions for the kind of general case, and these are the basis functions that we'll be interested in for the model problem because there are no degrees of freedom on the boundary in that case. Okay, so again, a picture is going to prove to be invaluable in this case, but let me state the theorem before we get on to that. Suppose that I have a triangulation of an open polygonal set omega, then this set of functions, BR, where we take phi I equals 1 to nr, is a basis for mr. And the set B0R, where I take these basis functions, remember these are the basis functions which don't have degrees of freedom at the boundary. Phi Ri superscript 0, that means interior. For I equals 1 to nr0, r equals 1 and 2, is a basis for m0r. Now, how do I prove this? You do it the same way you do in 1D. You show that every function can be written as a linear combination of these functions, and then you show that you have the span that's the spanning property, and then you show that you have the linear independence property as well. So you used to show spanning and linear independence in both of these cases. I'm not going to ask that you do this or worry about this. In some sense, it's not necessarily mechanical and super straightforward. It does require some steps. But once you know how to do that, and once you know how to do the one-dimensional case, then filling in the details of those steps is not too difficult. So we're not going to prove those, but hopefully once I show you what these functions look like, you'll say, "Oh yeah, that's kind of obvious. All right, and as a simple corollary of this, we know now what the dimensions of these two spaces must be. The dimension is exactly equal to the number of elements in the in the basis, right? So there are nr elements in the mr basis, nr elements, and so that must be the dimension of that space. And there are nr0 elements in the second basis, so that must mean that this is the dimension of the space M0R. And actually, this the way you can count things and the way you can figure things is a lot simpler than thinking about, well, how many elements are in the bases. This just turns out to be the number of nodes, just the number of nodes, as I'll show you in a second. And then this is the number of interior nodes for this second size of this second set. So once I show you a picture, I hope that you'll believe me that that makes perfect sense. But first of all, what do these basis functions look like? These basis functions are whenever r is equal to 1. So let's do the r equals 1 case. Let's do r equals 1 first. So these are the piecewise linear basis elements. So what you should think about is I have a mesh put down on my two-dimensional polygonal domain, and here are some of the vertices in that. And of course, the mesh keeps going outside of this. But what I'm really focusing in on is a single vertex here in the middle. And I'm looking around what triangles touch that vertex. Okay. What triangles share that vertex? Well, that's what we call the coordination number of that vertex. It's all the triangles which share that vertex in common. Okay, one of its corner points. So all the triangles that have as its corner point that thing in the middle there. So my basis function phi I, if this guy here is zi, then how would it be defined? Well, the basis function must be 1 at that point. It's 1, and it must be 0 at all the others. Okay? Well, that means that when I look at the triangles which touch this vertex in particular, then this basis function must look like a tent near that. Over those triangles, it's basically transitioning from 1 up to 0. From 0 up to 1, from 0 up to 1, 0 up to 1, and so on. So this is why we call this, even in 2D, this is called a tent function. Okay, it looks like a little tent. So what is the support of this function phi I? The support of the function, as you recall, is the closure of the set where this function is non-zero. So that's going to be these triangles down here, right? It's going to be the union of all the triangles such that zi is in all of those triangles. It's one of the vertices. Actually, we're taking the unions of the closures, and so that we get a closed set in the end. It's the union of all the triangles that have zi as a vertex. That's precisely what is the support of these tent functions. Now, why is this important? It's important because whenever we assemble the stiffness matrix, we have to compute these entries ij, right? And the entries ij are just the bilinear form where we put in phi j and phi I. So what we have to do is find where there's a non-trivial overlap of the supports of these two functions. That's going to dictate whenever this guy is essentially generically zero or generically non-zero. Okay, so let's consider this triangulation here. So now, if you do a bird's eye view of what these hat functions look like, or these tent functions, let's look at this one at zi here for a moment, right? So at zi, phi I is going to be equal to 1. So it's 1 here, and it's going to be 0 at all the other nodes, all the surrounding nodes, and all the other nodes as well. So basically, but what happens outside of its support, it's just identically 0. It's always just identically 0 outside of its support. Here's one ZK. What does this guy look like? Well, I've shaded its support in green. So its support is the set of all triangles which have ZK as one of its vertices. So that's that triangle, that one, that one, that one, that one, this one, and that one. All those triangles have ZK as one of its vertices. So the support of ZK is this whole set here. Okay, that's the support. Let's look at this basis function phi j, which is going to be 1 at zj and 0 everywhere else. What is its support? Well, its support is, that is where it's non-zero, is any triangle which has zj as a vertex. Okay, so this one, this one, this one, this one, this one, those 5 triangles. This kind of analysis this bird's eye analysis is useful for determining when phi ij is going to be generically 0 or whenever it's going to be generically non-zero. So let's look at that case where we have I and j. So is aij going to be generically 0 or generically non-zero? Well, it's going to be generically 0, phi I, a phi j phi I. There's phi j, there's phi I. And why is it generically 0? Well, their supports don't overlap at all. So that means, remember this, how is this defined? This is the integral of gradient phi j dotted with the gradient phi I. Well, the gradient of 0 is everywhere 0. So whenever this function is 0, its gradient is 0. So out here, outside of its support, it's always 0. It's only non-zero in here. What about this guy? So in here, its gradient is non-zero, but outside of its support, outside of that set, say out here, it's always going to be 0. So precisely where this guy, this hat function is 0, annihilates where this guy is non-zero and vice versa. So this guy has to be generically 0. So the way you configure it mathematically, you can always guarantee it this way. If I say the two-dimensional measure, or if I notice that the two-dimensional measure of the intersection of the two supports is 0, if I see that, then I know that this must be generically 0. So by this notation here, I mean the two-dimensional measure. So let's say that 2D measure, 2D Lebesgue measure, okay? So you know what the measure of a set is. It's just going to be its area. Now, if there's just, so you might argue, right? Support intersects support. Actually, that intersection is non-zero, right? It's non-empty. In fact, the intersection of those two supports is this point right here. But that's just a point. It's 2D measure. The 2D measure of a point is just going to be equal to 0. The 2D measure of a line is also going to be 0. So if I find the 2D measure is 0, I know that generically I'm going to have 0 for that entry. So I don't even have to spend any computational time worrying about it. Now let's look at phi j and phi k. There's phi j, phi k. Do they have a support, and is the intersection of their supports a set of measures 0? The answer is no. their intersection is kind of this brown set here. Okay, the intersection of the kind of lavender and green turns out to be brown. It's those two triangles. And therefore, this guy is not going to be generically zero. It's going to be, it might be zero, but we can't say that it's generically zero. Okay, it might be zero, but we can't say that it is generically zero. What did the piecewise quadratic basis functions look like? So this is the case where r is equal to 2. These guys are a little bit more radical and interesting, I think. So again, we're looking at a part of the triangulation, the mesh, and we're looking at this point here. That point we're going to call ZI. That's in the middle, ZI. And the other points are Z, but their indices are not I, right? So this guy here is phi I. So what do we know about phi I? It's going to be 1 at zi, and it's going to be 0 at all the other nodes. Now, in this case, these vertices aren't the only nodes that are going on here, that appear. There are also edge midpoint nodes. And notice that this basis function has to cut down, and it's going to cut through that, okay, these edge midpoint nodes, and it has to be 0 at those as well. All right, so, well, what does this mean? This means that this function is obviously not piecewise linear, it's piecewise quadratic. It's going to be a 2D quadratic function on each one of these triangles. Okay, now outside of these triangles, like out here, it's just identically 0. Just take the thing to be identically 0. But inside here, it's this complicated function. Now, I can't even draw the surface of this, but you can imagine what this surface looks like. The surface is along here, it's going to be linear. It's just going to be a straight line. The value is just going to be, well, 0 there. And then they kind of curve up like that. Does everyone see that? These are like isocontours. And same here. You've got 0 along there, and then you've got these isocontours going up. So it's an oddly shaped function, right? Well, it's kind of looks like kind of a tent function, but where the sides of the tent kind of drape inward. Now, those aren't the only kinds of functions, and this is kind of the analog of what we talked about in 1D. There are also these things called bubble functions in 2D. These bubble functions are one at edge midpoint nodes. So for example, this particular edge midpoint node here might be, let's call it zj, and then this is our bubble function phi j. And of course, I don't know whether this is going to be a 0 here or an unzero. Okay, so we don't have to worry about that. And also notice that I've, instead of putting the 2 here, I haven't put the 2. All right, so what was my, yeah, so here I will add a 1 or 2 to distinguish them, but then later on I'm dropping it. So for example, I could have put a 1 here because that's a piecewise linear basis function. And then later here I could have put a 2, but I'm just dropping that. Does everyone get that point? I'm just dropping the 1s and the 2s. Okay, so these are what these basis functions look like. These kind of draped tent basis functions and these bubble functions. All right, so 2D is a lot more complicated and kind of interesting, and so we'll get into that a little bit. So let's let Zj be equal to well, let's let Zj be the points of this set V0 union E0. So these are the set of all the interior nodes. Nodes come in two flavors, okay? Nodes can either be vertices or they can be edge midpoint nodes. The coordination number of ZJ is the number of triangles of of the mesh such that ZJ is, let's see, did I get that right? Is the number of, yeah, sorry. It's this number, coordination number, is the number of triangles of tau h such that ZJ, that have ZJ as a point. I see why I'm goofing this up, and that's because I'm missing a word here. Is the number of triangles of that, yeah. There we go. That have that as a point. In other words, it can be written in this set builder notation. So it's the number of elements in this set. It's the number of triangles in the triangulation such that ZJ is an element of K over line. So this is the closure of K. So it is a little bit different than what I have written in this word, what I have written in words here. You have to take the closure of the triangles. Okay. So let me see if I can explain this. Suppose I have this node here. Okay, so this is node number 25. What is its coordination number? It's the number of triangles that have that node either as a vertex or a midpoint edge, an edge midpoint node. So how many are there? There's one, two, three, four, five, six. So the coordination number of this um, 0.25 is going to be 6. And I have it written incorrectly here. Let's fix that now before I forget. There we go, 25. The coordination, that's the number of triangles basically that touch that point. What about 18? That's also one of the nodes in our mesh. It's not a vertex, it's an edge midpoint. What's the coordination number of um, that node? Well, it's going to be 2. So 1, 2. Triangle 12 and triangle 13. Okay, that's the coordination number. So this is an example. This is an example of a mesh where I've basically have 32 um, congruent triangles. Okay, so 1, 2, 3, all the way up to 31, 32. Um, and how many degrees of freedom are going to be in this mesh? Well, that's going to be the number of nodes that you see. And this is going to be for the model problem. Okay, so this is model problem, I should say. Model problem in 2D with r equals 2. So this is a piecewise quadratic case here. All right. Now, if r was only equal to 1, then this picture would simplify because we wouldn't put it in the edge midpoints. Now, so let's count up the number of nodes that we have in this mesh. Well, let's just count them in order that you see them. We're going to have 1, 2, 3, 4, 5, 6, 7. So that first row comes from these edge midpoint nodes. And then I have an edge midpoint, vertex, edge midpoint, vertex. It oscillates, right? And then back to just being edge midpoint nodes, edge, vertex, etc. So there are 49 total nodes in the mesh. That tells me exactly what the number of degrees of freedom, that tells me the dimension of the space, actually. This tells me that the dimension for this case of M02 is going to be exactly equal to 49. Okay. Now, how many basis functions of each type are there? Okay, well, that one you can pretty easily figure. There are going to be, let's count the number of basis functions that are subordinate to these vertices first? Well, there are 1, 2, 3, 4, 5, 6, 7, 8, 9 of these interior vertices. So there are going to be basis functions for each one of those. So that's 9. That means the other 40 are going to be the so-called bubble functions. There are a lot more bubble functions in this case than there are these basis functions associated to the vertices. Okay, and so you can keep playing this game and do the countings this way. Let's have a look at some elements, okay? The elements of the stiffness matrix. So we want to start assembling the stiffness matrix in a coherent, consistent way. So for example, let's figure out, is there going to be an entry of my stiffness matrix in row 25 and column 18? Well, what we mean there is there going to be something, is this entry going to be zero generically or non-zero? So for 2518, we're going to have to look at the support of phi 25 and phi 18. So here's 25, and the support is in this light green, mint green, okay? So it looks like that. It's going to be 1 here, and it's going to be 0 at every other node. Now, basically, it only has a kind of interesting pattern within its support. Outside of its support, you just set it entirely equal to 0, okay? So that's phi 25. What about phi 18? Phi 18, phi 18 has a much smaller support. Its support is only over these two triangles, triangles number 12 and triangle 13. So does is there an entry in 2518? The answer is yes, generically yes. Now it still may work out to be 0, we don't know, but we say that it's generically non-zero because the measure of the intersection of the supports between 25 and 18, which turns out to be precisely the union of triangles 12 and 13, um, well, actually, let me be really precise about it. It's the union of the closures of those. So the measure of the union of the closure of K12 and K13 is definitely not 0. So this is generically non-zero. But what about 1625? So again, there's 25. Let's go find basis function number 16. Well, basis function 16 would be 1 at this node, and it would be 0 at all the surrounding nodes. It's a bubble function. So there's no intersection between its support and the support of phi 25. Actually, that's not true, right? There is an intersection. It's that edge, but that edge has two-dimensional measure 0. So generically, this guy is going to be 0. All right, so I'm going to review, let's see. I'm going to review this, a general procedure for um, doing a finite element method in 2D. Um, but before I do that, I want to take a break and take your questions. Okay, so now I want to review kind of a very generic procedure for how we're going to make FEM work, finite element method work in 2D. And well, the idea is that we'll come back later and fill in all the particulars of this, well, at least some of the particulars of these details. Some of you may be interested in writing a finite element code. Some of you never ever wanted to think about doing such a crazy thing. So it's nice to know and put these types of things in the back of your back pocket just in case you ever want to do something like this. Nowadays, with things like ChatGPT, though, I mean, putting together a code or Claude or some of these other generative AI tools, putting together a finite element code is probably not the daunting task that it used to be whenever I was younger. But anyway, we're going to look at this at a very high level. We're going to look at some of these details at a very at a lower level, and then we're going to move on from there and talk about the uh, the approximation theory problem in the finite element method. Okay, so what would you need in order to do finite element computing in 2D? Well, you're going to need to know what is the shape of your omega. You're going to need to know what is the forcing function. So let's just think about the model problem for now. The model problem, the only data in the problem is just going to be the f, the forcing function, and the geometry of the problem. There's not really anything else there, but this is enough. This is complicated enough. The next thing you're going to want to do is to compute a triangulation for phi. What do I mean by computing a triangulate or constructing a triangulation? Well, so then you have to have some sort of back end. Let's say I have a complicated shape like the state of Tennessee, and I want to put a mesh on the state of Tennessee. How would I do something like that? It's complicated. It's a complicated shape. Well, there's some tools out there, but if it's a very simple geometry like a square, there are very simple rules for doing things like this. So you should think about it in these terms that if it's a complicated domain, I could always go out and find a mesh generating tool to build me my mesh. And if it's simple, I could do it by hand myself. So that's the step where you have to construct the mesh. And remember, we have to keep in mind the rules. We have to build a good and true triangulation that doesn't have any hanging nodes, for example. Um, then the next thing we need to do is compute the so-called local or elemental stiffness matrix and the local or elemental force vectors for each triangle. So this will take some explaining. So I need to explain this. What do I mean by the local stiffness matrix rather than the one that we've already been dealing with? What do we mean by the local force vectors uh, in contrast to the global force vector? Well, once I have these so-called local stiffness matrices and those local force vectors, I can do mapping to help me do a process called assembly. So I'm going to assemble the global stiffness matrix and the global force vector from these local ones. After that, I have a problem to solve. Now, you don't always just throw this so one thing I will point out is you're going to have a matrix which has a lot of zeros in it. What we call that a sparse a sparse matrix problem. And the idea with a sparse matrix problem is you don't necessarily want to store all those zeros. So I might not want to just throw this into MATLAB. For example, I might be solving a problem which has a million degrees of freedom, meaning that this vector has a million unknowns, and this matrix A has a million rows and a million columns. So I might not want to throw in all those zeros in there that are going to be in there in that sparse matrix. I might want to take advantage of some structure so that I don't have to do something really complicated. And then the last step is usually what we call the post-processing step. So I really want to try to make you understand or help you understand a lot of these steps. We're not really going to talk about mesh construction in this class. That's a complicated course all on its own. However, we are going to talk about how we assemble the stiffness matrix from the local stiffness matrix and how we assemble the global force vector from the local force vectors. We're going to talk a lot about that. What about solving these problems? Well, I just got done teaching a full course on this topic called the multigrid method, where we talked about solvers for these types of problems. So if you took that course, bravo. If you didn't, the good news is there's a book coming out. We just finished our book and it'll be out in December, and you can read all about all of the techniques that we developed for solving problems like this. Let's look at what we call the local stiffness matrices. Let's motivate those and help you to try to figure out what these things are. I need to develop a few components before we get into the details of what is the local stiffness matrix. But I think what you're going to find is that things are going to start becoming kind of clear as we build this up. So suppose I want to compute the ij entry of my stiffness matrix. Now this is the global stiffness matrix. So let's start off by being very clear. We're talking about the global stiffness matrix here. So we want to come up with an algorithm which works really well for assembling the elements of this. Remember the definition of a ij is a phi j phi I. And remember, I've dropped, this could be a 1 and or a 2 here. I'm going to drop that. I'm not going to make those distinctions. By definition, this is an integral over the whole polygonal domain omega of the gradient of phi j dotted with the gradient of phi I. Well, remember we said that that this really only has something happening in the intersection of the supports of these two functions. That's because where these functions are 0 kills off where anything else happens in the other function entirely. So let's first think about writing this slightly in a slightly different form. So how could I rewrite this integral? Well, I can use the fact that Lebesgue integration, for Lebesgue integration, I can write this as a sum of integrals over subdomains. I can write it as, in particular, the integral, or the sum of integrals over each triangle for all triangles in the mesh. Okay. Now, not all the triangles in the mesh are going to be in play though, because we're only really going to have to worry about triangles that are in the intersection of the supports, right? So here I mean SI is by definition the support of phi I. And of course that means SJ is by definition the support of phi J. Right? I only have to look for triangles that are in those intersections. But the important point here is that I can take this integral over this whole domain and break it into integrals over triangles. Okay, so let's look at our an example that we had previously. For the case where we had these piecewise quadratic approximations, let's compute the 2518 entry of the stiffness matrix A. By definition, it's equal to A phi 18, phi 25. And that's from this example here. Here's phi 25, and there's phi 18. By that, I mean there's node 25, and phi 25 is 1 at node 25, and it's going to be 0 at all the other nodes that you see. Okay, all the other nodes that you see, it's 0. And it's identically equal to 0 outside of its support. So outside this set, phi 25 is identically equal to 0. Now, what about this guy here? Okay, so this is the support for this function, phi 18. It's a bubble function. So its support is only these two triangles, and outside of that, it's identically equal to 0. That's why we take the intersection of the supports, take the intersection of the two supports. So what is the intersection of the support for phi 18 and phi 25? Well, it's precisely triangle 12 and triangle 13, which is what I have written here. Triangle 12 and triangle 13. I want to beat into your brain that really what I'm going to be interested in when I compute the entries of a stiffness matrix is just a bunch of a bunch of repetitive types of calculations, integrals of two basis functions over a triangle. Now, what two basis functions could come into play? Well, there's only, if I look at a triangle, it's only going to be basis functions which can have non-zero support over that triangle. So I need a way of keeping track of that. So for example, if I look at triangle 12, what basis functions could have a non-zero support over that triangle? Well, or in other words, that this triangle is part of the support of what possible basis functions? Well, there could be 25 and 18 as I have here, right? Or 25 and 11, or 25 and 17, 23 and 24. You can see there's all possible combinations. This guy could be in the intersection of the supports of a bunch of different triangles. So what I'm going to do is I'm going to calculate what's called a local stiffness matrix associated to each triangle, and then I'm going to reassemble them in the global stiffness matrix. That's a complicated thing to do, so I have to prove to you that it can be done. What about 13? Triangle 13. Well, what basis functions can have a non-zero support on that? Well, 25 and 18, as I've indicated here, but also 19 and 11, right? They could also have a non-zero intersection for sure, and lots of other combinations as well. So when I compute what's called the local stiffness matrix, I'm basically taking all of the basis functions that are associated to this triangle and I'm combining them together. Well, I need to know, so if I've got it drawn out like this, it's very easy to see what's what. But what I really need to know and what makes life a lot easier for me is if I have some sort of definite mapping about what nodes are in what triangles. Okay. So for example, I might need to know or might be interested to know that, well, triangle 13 has what nodes in it? 11, 12, 13, 18, 19, and 25. Okay. So I might want to know um, that the local node. Okay, so now I could break these nodes into local nodes and global nodes. So I could number the local nodes as 1, 2, 3, 4, 5, and 6. So there's 6 local nodes in triangle 13. I might want to know that 11 is the global node 11 is local node 1 and global node 12, sorry. Yeah, global node 12 is local node 2 and local node 3 is global node 13 and so on and so forth. So I'm going to get into all the details of that. But let's do another simple example. What about A1812? So this is going to be by definition the integral over omega of gradient phi 12 gradient phi 18. So where's 12 and 18 at? So there's 12 and there's 18. So 12 is a bubble function, and what is the support of that guy? Well, it's that. I guess I've got it drawn down here. Yeah. So 12 is the bubble function that has that support. It's 1 at that node and it's zeros at all the others. And what about 18? Well, that's a bubble function that's 1 at 18 and it's zeros at all others. So its support is here. So what's the intersection of the supports? The intersection of the supports is going to be triangle 13. So really I only have to compute this element, okay, or that part. So what I'm going to do is I'm going to, when I'm putting together a code, I'm going to compute all the combinations like this. I'm going to look at all the triangles and I'm going to compute all the possible combinations of all the, well, I don't have to do the global nodes. I could just do its local nodes and I can store those up. That's called the local stiffness matrix. But don't worry about that now because that definition is coming um, more clearly, I hope, in a bit. So to do this process, what we need are a bunch of arrays that represent the mesh. So just to show you that meshes don't have to be clean and nice, they could be quite ugly. So here's a mesh which is ugly, but it's still it's a triangulation of a square, well, a rectangle, but it's a good triangulation. There aren't any hanging nodes in there that I have to worry about. Now, for this case, I'm only going to be interested in the vertices for now. And that's because I can build in the information for the edge midpoints later. So my matrix Z is going to contain the coordinates of all my vertices. The way this usually works is you cluster things. You're going to cluster all the interior vertices first. So there's only 4 interior vertices. I'm just going to give each one of these has what an X and a Y coordinate, right? So I'm going to break that into the X and Y coordinate, right? So there's the coordinates for node 1. For node 2, there are its coordinates. Node 3, there are its coordinates. Node 4 there. So I'm going to cluster all the interior nodes first, or at least all the interior vertices first. And then I can cluster the boundary vertices next. And I'm just going to count those this way. So sometimes you don't have a ton of control over stuff like this. Your meshing program is going to develop or going to give you this information. And you're going to have to decide or know, is it on the interior or on the boundary? In the interior or on the boundary? Well, you can write a little script, hopefully, that can shuffle things around for you and cluster the boundary nodes or boundary vertices at the end and the interior vertices at the beginning. Now, again, thinking about this mesh here, I need what's called a T mapping. And the T mapping tells us so it tells us what points, what vertices are in what triangles. Okay, so for triangle 1, where is triangle 1? Triangle 1 is here. And usually there's some numbering convention, but it really doesn't matter uh, as long as we agree to always number in counterclockwise order. So triangle 1 has node 5, 1, and 16. Triangle 2 has what nodes? 6, 1, let's see, 6, 1, and oh, I made a mistake there, right? It should be 6, 1, and 5. What about triangle 3? 6, 7, and 1. That one's okay. What about triangle 4? That's this guy here. 1, 7, 2. Notice that I'm always numbering in the counterclockwise direction. So you can go on like this. For each triangle, there are 18 in my mesh here. The last one is going to be 4, 10, 11, I think. Yeah, 4, 10, 11. So T gives the local to global mapping of vertices. All right, so we're going to start. I'm out of time, so we're going to pick up with this more when we meet again on Thursday. But let's take one last example. Look at triangle 10. Triangle 10, if I pick it out from the mesh, has the following vertices in it. It has vertices 2, 4, and 3, right? 2, 4, 3. And you can go back up and you can find that 2, 4, 3. Now, in that triangle, I have what are called local vertices, which are also numbered in a counterclockwise direction, and I have global vertices. So what I'm really saying is when I write down that mapping that I have above, is I'm telling you what are the local to global node numbering mapping. So for example, uh, T210, that's going to be what? So this is really a matrix. So if I'm looking at row 2, column 10, that's going to be 4, right? That tells me that local number 2, vertex or node 2 in the triangle number 10 is global number 4. So this tells us how you map back and forth between local nodes and global nodes. So this is what we call the local to global mapping matrix. And we're going to pick up with that next time. So I'll end the lecture there and I will take any questions you guys have.